Hi everyone, welcome back. Today we are going to be talking about thermodynamics or thermochemistry, and that kind of relates into how does energy and work and all of those things interrelate. How can we use chemistry to produce energy, and how much work can that energy do on a system? So we're going to talk a little bit about thermodynamics. Now this gets into physics very quickly, so we're going to leave it pretty vague, but we are going to get into it a little bit. All right, so let's get started. All right, so first thing is that we need to get a couple of definitions down. So energy, when we talk about how energetic a reaction is, usually we're talking about heat, right? Exothermic or high energetic produce a lot of heat, but it can also relate to how much work something can do. So if we have a lot of energy, it could do a lot of work, or it could do heat. Well, that kind of gets us into what is work, and we're going to get into work in a second here. Now, there's a couple of different types of energy. The first is potential energy. Okay, so potential energy is essentially the potential of the chemicals, or the energy stored into the chemical bonds, which is the composition. Right? And then the other type of energy is kinetic energy, which is the energy of motion. Temperature is directly related to kinetic energy. That is the equation right there for kinetic energy, right here. This is the equation for kinetic energy. You don't really need to know this at all. Just know that mass and velocity are part of kinetic energy. So we could have a very heavy particle moving slowly, and it would have the same kinetic energy as a very light particle moving very fast. Okay, so they are related. All right. So law of conservation of energy, just like the law of conservation of mass, the law of conservation of energy says that energy can't be created or destroyed. All right, we can change it, we can convert it, from potential to kinetic, and vice versa. But the total energy has to stay constant. So from the beginning of the universe to the end, or whatever have you, the amount of energy is constant. Right, and then we're going to kind of tie this into the first law of thermodynamics. We're not going to learn all the laws of thermodynamics, but this is just the first law. Like I said, the energy content of the universe is constant. It always has been and always will be the same amount, which gets into some crazy things because the universe is constantly expanding, so you're spreading the same amount of energy over a different area. But talk to your physics teacher about that, because that's kind of wild and crazy. All right, we're going to talk briefly about state functions. State functions are a little odd. Okay, so a state function says that it depends only on the present state of the system. So it doesn't matter how I get there or where I go. It's just defined by the state. So for example, let's say someone's standing on the top of Mount Everest, or let's say there's a boulder on the top of Mount Everest. That boulder on the top of Mount Everest has the same potential energy, whether it was rolled up the side, or whether someone dropped it there, or whether it was like broken down and carried up in little chunks and reassembled. It has the same amount of potential energy. So a state function means that regardless of how you get the end result, regardless of the mechanism, it's the same. Okay, so regardless of the mechanism, energy is the same. It's called a state function. We're not going to get too much into it. Now, work is not a state function. Okay, that means that the amount of work done on something is dependent on how you get there. Right? Let's say you had this little hiker at the top of Mount Everest. We're going to assume there's a hiker up there. I don't know. It looks like kind of a fake flag. But anyway, so let's say there's a hiker up there. It would have taken a lot more work if he had taken a jumbo jet and parachuted out, right? That would have taken a huge amount of energy to move that jumbo jet with only one person in it. It would have taken a huge amount of energy. That would have been a lot more work than like a little Sherpa carrying him up the side. Okay, so I don't know why in this example the hiker can't hike his own way up there, but so work is not a state function. It depends on how you get there. The amount of work depends on how you get there. How you got to school or how you got home, the amount of work is dependent on what car it was, right? If you drove a big 18-wheeler home, that took more work, right? More energy than driving a little smart car, one of those tiny little smart cars. So work is not a state function. Now here's the equation. The change in energy, and we get into some fun letters here, equals Q plus W. Now Q is heat. Okay, so Q is the heat flowing into or out of the system. So We'll get into that in a second. So it's negative if it's leaving the surroundings. Now this leaving to the surroundings. I'm sorry. It's negative if it's leaving to the surroundings. Now this gets a little weird because that's a hot reaction, right? So if we have an exothermic reaction in our beaker, it's producing heat. The heat is leaving to the surroundings, and that's usually the air or you or the thermometer. So the heat is leaving to the surroundings. You have a negative heat because heat is flowing out of your beaker. Okay, it's counterintuitive because you're like, no, that beaker's hot, so that should be a positive Q. Now it's negative because the heat's flowing out. You have to think of it in terms of what's the stuff inside, the chemicals or the solution inside. It's flowing out of the solution. It has less heat. And then Q would be positive if it's entering in, if it's coming in. Okay. Now W is obviously work. And that's done by the system, on the system, for the system, all that other stuff. And we're going to get into what exactly work is. Now, work is negative if it's done by the system. So once again, if work is essentially leaving the system to the surroundings. So if work's done by the system onto the surroundings, so if work is going from the system to the surroundings, it's going to be negative. Same with heat, okay? And then if we're doing work to the system, if we're inputting work, then it's going to be positive. Because this delta E is reference to what's inside that beaker. So if that beaker loses heat, meaning it gets hot and the heat leaves, Q is going to be negative. And if that heat does work on something, the work will be negative. Okay, so then work is related to pressure and volume. All right. Now think about this. This always helps if you think about it in terms of like a car's engine. Okay, so in a car's engine, you have a piston and it moves up and down. All right, and when it's down, gas goes in, and there's some oxygen, and there's a spark, and it explodes, and then the piston moves up. All right, essentially, right? Don't quote me on this. I'm not an auto teacher. I don't know much. I can replace a headlight, is my claim to fame. So the piston is lowered, and then you inject fuel and air and a spark, and it explodes, essentially, mini explosion, and it forces the piston up. That would be expanding. So in that case, the volume would obviously be increasing, and the pressure would be decreasing, right? As it's expanding, the pressure would go down a little bit. So the volume would increase. We would have a negative work resulting, right? The work is flowing out of the system, right? It's the little gas vapor is doing work on the piston, making the piston move upward, and the energy decreases. That makes sense, right? The gases coming out of the exhaust pipe have a lot less energy than the fuel going into the car because they expended all their energy doing work in the engine. So work has been done by the system on the surroundings. Now, let's talk about compression. Now, compression is going to be the exact opposite, right? So don't think about a car. Think about anything else. That's not a car. I can't think of anything off the top of my head. I'm not very mechanically. So in compression, we are compressing something, right? So the volume is decreasing. That means volume is negative. Well, if volume is negative, all right, that means that we're going to have a positive work, right? Because volume is negative, so it's going to make work positive. That means the energy increases. Well, that makes sense. If you take a canister and you press on it and you squeeze it down, you're essentially adding energy, right? If you take something, the energy from your hands is going into the system. You can kind of think of it like that. Work is done on the system by the surroundings. Okay, so work is this idea of pressure and volume changes. It's kind of a weird idea. All right, the last thing we're really going to talk about tonight, or today, I guess. It's nighttime by me. It's like 10:15. But you might, I don't know when you're watching this. You're probably watching this much later than I am making it. Anyway, you've seen these diagrams before. You've seen these big old diagrams before. This one is endothermic, right? This is endothermic. That means that heat is coming into the system from the surroundings. So we have a positive heat flow into the system and a negative heat flow from the surroundings, right? Because it's going from the surroundings into the system. So if the surroundings had 5 units of heat, it would lose all 5 and the system would gain them. Because, see, and it goes in and we have more energy when we're done. And that delta H, that change in heat, is related to Q. Not exactly the same thing. There's a couple of different constants that we kind of got to multiply them by and how we have to change them slightly because heat isn't exactly delta H. Delta H is, but we'll get into that. The next one you might be shocked to see is exothermic. So in an exothermic reaction, notice we are losing energy. So heat is flowing out of the system and it's going into the surroundings. And the surroundings in this case would be like your hand or a thermometer or your lab part. I don't know. So anyway, so I hope that kind of cleared things up. That's the idea of energy work. It's kind of an odd thing. It really gets into physics and engineering very, very quickly. So we don't spend a ton of time with it. That we're more of like a pure theoretical inorganic chemistry. But it's there if you need it and love it, and I hope you do. So, all right, I will see you all in class.